All right, so let's go through an example that illustrates how you would use 1D optimization in the context of a statics problem. So here we're going to do example 4.4 from the text. So you can see the problem statement here. We have this belt tensioner that's attached to the engine at this point A, so it rotates around A. And if you want to release the tension, then you would apply a ratchet wrench here at the end of the belt tensioner, so at point C, and then you could sort of pull on that, and that would release the tension on the belt. So the moment that's required to actually release the tension is 50 Newton meters, and the questions related to what would be the angle that we should apply the wrench here? So what is alpha, such that we can use the least amount of force to reach that moment? So you can see some dimensions. You can see the wrench is 300 millimeters long. Alpha is this angle that we're going to figure out. The tensioner is 250 millimeters long, and then its angle relative to the x-axis is 30 degrees. And there's two cases we're going to look at. The first case is when this force F is perpendicular to the handle of the wrench, and the second case is where F has always got to be horizontal, so in the x-axis. So that's the problem, and I guess you can maybe go off and try it and then come back and we'll go through the solution together. Alright, so the solution that we're going to do is going to use a vector approach, and it's also going to set this up as an optimization problem. So the idea then is that our independent variable is going to be alpha, that angle, and we'll let the optimizer and EES choose the value of alpha that minimizes the force. So let's go ahead and think about the governing equations before we try to do this in EES. First thing I'm probably going to do is define a position vector RAC that corresponds to the tensioner, and that should be pretty easy. I know the angle and the length, and then I'll also define a position vector RCD that corresponds to the wrench, which is also pretty easy because I know the angle alpha, or at least I will be varying that if I'm doing an optimization, and I know the length of the wrench. And given those two position vectors, then I can define a position vector between point A, which is the bearing, and that's the point we're trying to determine the moment around, to point D, which is the location where the force is applied. And that's just this equation where I'm adding those position vectors. All right, so in part A, the force vector is perpendicular to the wrench, and therefore if I know the magnitude of the force, I know its direction based on this angle alpha, and then I can get the moment that the force vector applies about the bearing, about point about point A, as just the moment is RAD cross F. So that moment is a vector. It's a vector in the z direction. We want to make sure that the force, the magnitude of the force that we apply is set such that the magnitude of that moment is 50 Newton meters. And you can see that it's in the clockwise direction, and therefore it would be actually minus 50 Newton meters. All right, so with the governing equations kind of set up, we'll go ahead and open up EES and try to enter them and carry out the math. So I am going to be using some angles, so I'll use the dollar unit system directive, first of all, to specify that we want to be using degrees for the angles. And then I'll put in the inputs. So the inputs are the tensioner angle and its length, and the wrench length. And then I'm also going to specify alpha is 20 degrees. This is an arbitrary number that I'm going to eventually comment out in order to have a degree of freedom to do the optimization. All right, so I have, let's see, 3 position vectors. They're all 2D vectors. This is a 2D problem, so I'll define them to be 2D vectors. Those are RAC, RCD, and RAD. Let's see, RAC and RCD we would assign using the vector assign polar commands to know the magnitude and the angle. So you can see here the magnitude of RAC is the length of the tensioner, and its angle relative to the x-axis is theta. Within RCD, the magnitude of the wrench position vector is LW. And then because alpha is defined relative to the y-axis, its angle relative to the x-axis is 90 degrees plus alpha. And then RAD, which is this position vector going from point A to the position where the force is applied, is just the sum of these two position vectors. All right, and then for this first part where the force is defined as being perpendicular, I know its angle, right? So I'm going to use the vector assign polar command in order to define the force vector. So the force vector has a magnitude mag f here, which I don't know, it's still an unknown, but its angle is alpha. That's the angle it would have if it were perpendicular to the wrench. And then the moment is just the vector cross command of RAD cross f, right? And because these are all two-dimensional vectors that I'm using, the moment is actually returned as a scalar. It's just understood that it's going to be in the z direction. So I'm going to then set that to minus 50 Newton meters. And if I solve now, then I can get a solution, right? There are no degrees of freedom because I've set alpha, and the solution says that for alpha equals 20 degrees, the force required to get this moment is 145.6 newtons. So the question asks for the value of alpha that minimizes f, and so this is an optimization problem, a 1D optimization problem. So the first thing I'm going to do is comment out the value of alpha that I set here. And now if I go to select min max from the calculate menu, I'll bring up the find minimum or maximum dialog here, and I'll set this up as an optimization problem. So I want to minimize the magnitude of f, and my one independent variable is alpha. And I'll set some bounds. Maybe I'll go from minus 180 degrees to 180 degrees. That'll be the parameter space for alpha that I look at. And probably won't change anything else here, and hit OK. And it will tell me that the smallest force that I would need is 90.91 newtons, and that will occur if I set the wrench angle to minus 60. And this matches the results shown in the textbook. All right, if I want to do part B, where the force is horizontal, all I have to change is one line in this code. So instead of assigning the force vector using the vector assign polar command, I'm going to assign it now using vector assign. And I'm just going to specify that the y component is 0 and the x component is the magnitude of the vector. Otherwise, exactly the same. So carry out the optimization in the same way. I won't change the bounds or anything. And I find out that in this case, I need at least 117.6 newtons, and that will occur when alpha is 0 degrees. And again, this is also consistent with the answer from the textbook.